Hello everyone, I'm Aditya Bandopadhyay and welcome to this sixth lecture in which we're going to study system of nonlinear equations and Newton's basins of attraction. Okay, so first let us try to motivate how systems of nonlinear equations can arise in your studies. So consider you're a chemical engineer and you're interested in a particular reaction. So you have a tube like this and benzene, that is C6H12, C6H6 rather, it comes in at a certain temperature. So it comes in at 1400 Fahrenheit and it undergoes various decomposition reactions. So the first reaction that it undergoes is C6H6. It decomposes to C12H10 plus H2. Then C6H6 plus C12H10, they react to give C18H14 and H2. So this is called as biphenyl and this is called as triphenyl. So benzene, it decomposes into a mixture actually of benzene into a mixture of biphenyl, triphenyl and hydrogen. These are the different products as a result of thermal decomposition. So now let us try to write down the various reactions. So we have two equations. So let this be R1 and this be R2. So R1 is the rate at which benzene decomposes and it is equal to some constant times an Arrhenius factor. It looks something like this. So it's Arrhenius factor which depends on temperature times the partial pressure of benzene square minus partial pressure of diphenyl partial pressure of H2 divided by K1. Similarly, R2, that is the rate of decomposition of benzene through this reaction, okay, this is equal to some other constant. So let me call this K1. So this is K2 times exponential of some another Arrhenius term actually times. So this will be P hydrogen, or rather the forward reaction will be P benzene P diphenyl minus P triphenyl times P hydrogen divided by K2. So this is how the reactions they look like. Okay. So let us say that let us consider only the mole fractions. Okay. So considering that 1 mole fraction of benzene enters into the system. So if x1 moles of biphenyl and okay, so suppose x1 moles react from here and x2 moles react from here. So the moles of benzene, the mole fraction of benzene that will remain will be 1 minus x1 minus x2. That of biphenyl will be A times x1 upon 2. So let us balance this reaction. So there will be 2 over here. Okay. So 1 mole of benzene would decompose into half a mole of biphenyl. So that is why this x1 upon 2 occurs. And eventually x2 moles of uh, benzene would react with biphenyl. So x1 minus x2. This will be, instead of A, it will be 1. So these are the mole fractions of benzene that remain. These are the mole fractions of biphenyl. So triphenyl, you get x2 moles. Okay. So triphenyl will be x2 and hydrogen will be, so over here it will be x1 upon 2. So hydrogen, it will be x1 upon 2 plus x2. So then at equilibrium what will happen is the reaction rates will become 0. So at equilibrium R1 will be equal to 0 and R2 will be equal to 0, and this implies Pb square is going to be equal to Pd times Ph upon K1. Similarly, Pb times Pd will be equal to Pt times Ph upon K2. Alright, so this implies that, so we make use of the fact that the partial pressure of benzene, diphenyl, hydrogen and triphenyl will be proportional to the mole fraction. Okay, so this square will be proportional to 1 minus x1 minus x2 whole square, and this will be equal to x1 upon 2 minus x2 times pH will be x1 upon 2 plus x2 divided by K1, and the next reaction, it will be Pb, so that is partial pressure of benzene, times Pd, so that will be equal to x1 upon 2 minus x2, and this will be equal to x2 multiplied by the partial pressure of hydrogen, and all this divided by K2. So in order to find out how many uh, moles in equilibrium that we will get, we need to solve this equation and this equation simultaneously, and solving that simultaneously requires you to solve this nasty looking nonlinear equation. So that's how these equations are quite relevant to any studies which involve a bunch of chemical reactions, a sequence of chemical reactions. Okay, so in fact, let us proceed. Uh, so let me execute this first cell. This first cell is something which is going to be common, and so we're not going to sweat it a lot. So it's import numpy and import matplotlib and update the RC params of matplotlib and the inline rendering to be SVG, so that the plots in Jupyter Lab, they look much better. So let me execute this. So let us try to solve the equation, the system of equation. So let me write it down. So it will be x e to the power x plus y minus 2 and xy minus 0.1 exponential of minus y. So this could be a model for some set of reactions as well, but essentially we want to find out the roots of this. So both will be equal to 0. Okay, let us first make use of the library functions in Python, and later on we'll see how we can encode this, and we'll try to see how we can get some insight when we write the code ourselves. Okay, so let us import scipy dot optimize as sco. Okay, let us define the functions. So define system of sysfunc. It will take as an input x. So here x will be a vector, and that vector will comprise of x0 and x1. Okay, whenever we're doing sequence of a series of equations, we will give as an input x, but here x will not be a scalar, rather x will be a vector, and the vector components will be x0 and x1, because the indexing in Python starts with 0. Okay, Is the same with C as well. Okay, so now we must return an array. Okay, we must return an array. So the first element of the array will be this x naught multiplied by exponential of x naught plus x1, because y is equal to x1 and x naught is equal to x. So over here this is equal to x and this is equal to y. Okay, this is something which we will keep in mind. Apart from this, it will return the second set of equation as well, which is x naught times x1 minus 0.1 times np.exp of minus x1. All right, so once we have this, let us say sol equal to sco dot fsolve. We will pass the function handle, that is sysfunc, and we will give some guess values. So the guess values will be in this case 1 comma 1. Okay, so let me execute this. So there's a runtime error. It says the number of calls to the function has exceeded 60. Okay, so let us see whether we have input something incorrectly. We have forgotten to put -2 over here. Okay, so there was an offset, and once I added the correct equation, I had forgotten to write this -2. Anyway, so it executes. Let us see what let us print out what sol is. So print sol. Let us print out. So sol is equal to 0.8021 whatever it is and 0.111. So we can verify whether this is the solution by substituting this array into system of equations. Okay, so let us find out. So x sol comma y sol is equal to sys or return value of x naught, return value of equation 1, return value of equation 2 equal to sysfunc of sol. Let us print what the return values are. re1 comma re2. So it's 10 to the power minus 15. So obviously whatever we have over here is a solution of the system of nonlinear equations. Okay, so this is how you can sort of pass on the function handle to the fsolve solver, which is inside the submodule optimize of SciPy. It's a very easy thing to do. But now let us try to encode this particular program ourselves. So we will do it using a fixed point iteration, and let us first devise how we can form this particular fixed point iteration. So over here we have x e to the power x plus y equal to 2, and the other is equal to xy is equal to 0.1 exponential of minus y. So the first equation that we can form is x is equal to 2 upon e to the power x plus y, and the second equation will be y is equal to 0.1 upon x exponential of minus y. So this seems like a fair approximation. So let us define okay, so let us define the right hand side of this particular function. So let us define gx of x, let us just call it g. Okay, so it will return two values. So the first will be 2 times np.exp x, so minus of x0 plus x1. Okay, so this is the first value that we will return. Second value will be 0.1 divided by x naught times np dot exponential of minus x1. So these will be the two return values. Okay, so we're done with the function. Before trying to solve all this, let us first plot the two functions. So how can we plot these two functions? So keep in mind, these are not explicit functions, these are rather implicit functions. Okay, we want to find out, say, the root of this. Essentially, there will be some curve, some curve which will be defined by this equation. Let us say it is this curve. Some curve which will be defined by this equation. Wherever they intersect, that is the root. But let us first try to plot these things. But because they are not explicit functions on their own, we must find out an implicit way of plotting it. Okay, this is something which is quite useful, and it will be quite useful for many other works. Let us define x equal to np dot linspace, say 0 to 1, and y equal to np dot linspace 0 to 1. Then what we will do is we will define the mesh grid. So x comma y is equal to np dot mesh grid x comma y. So what it does is, if we have a linspace like this, so suppose this is x, okay, these are all values of x, and we have a array like this, so these are all the values in y. So the mesh grid, so capital X and capital Y, will contain all the inside intersection points. Okay, it will contain all the inside intersection points. So this is what all the inside intersection points will be assigned to x. So all the x coordinates of all these points will be inside capital X, and all the y coordinates of all these intersection points will be in capital Y. Okay, so in fact, let me just run this much and show you what x and y are. So look, across, as we move along columns, the x increases, but as we move along rows, the x does not change. So it means that when you move along rows, it has the same x value. But if we print y, we will see that as we move along rows, the y value will change, but as we move along columns, the x value remains constant, the y value remains constant. So I hope this gives you an idea of what a mesh grid structure looks like. So it gives you an output x and y. Let me delete this cell. So once we're done with this, we'll try to create an implicit function of these two things, meaning we'll create a level set. This is called as creating a level set. So let me create the first level set. It will be clear what it means. So f1 is equal to x star np dot exponential of x plus y minus 2. f2 is x times y minus 0.1 times exponential of minus y. So these are two levels. Okay, so capital F and capital Y are two functions. So depending on the value of f, so suppose f were to be 0, if f were to be 0, if I try to plot the isoline of f1, where all the points along this curve correspond to f1 equal to 0, so this is an isoline. Along this curve, all the values of f1 will be 0, and if all the values of f1 are 0 along this isoline, it means that it is the curve that we are looking for. So you do an implicit declaration all over the mesh and try to find the isoline of that particular level set. f1 is called as a level set function. Similarly, we'll have another level set function, say like this. So this will be the isoline of all the points on the curve where f2 is equal to 0. Okay, so let's do that. Let us do the isoline. So the way to do it is plt dot contour. So x comma y comma f1. If I simply do this contour, it will give me a family of curves for f1. it will give me a family of curves for f1, meaning I will have all the different family of curves for different values of f1. So this isoline is for some particular value of f1, this isoline is for some particular value of f1, and so on. But I am more interested in finding out the isoline for f1 when it is 0. So by specifying that I only want that isoline, I can plot only that single curve. Alright, similarly, I would like to find out the isoline of x comma y comma f2 and the 0 curve. Alright, so over here the intersection point is very close to 0.8, and that's fair enough. The first intersection point was in fact near 0.8 and the y value is 0.11. Let us see. Great, the y value also seems to be something close to 0.11. So the intersection of these two curves in the plane gives us the root. The root is the pair xy where the two curves intersect. Alright, let us now write down the fixed point iterations as we have defined over here. Excellent. So let's define the number of iterations. So n iter equal to 100. Let us say x. Let us define x as np dot zeros, and over here the size we have to specify. So it will be n iter comma 2. So we'll have n iter number of rows and 2 columns. Okay, we will save each pair inside this. We will declare x 0 comma all as the initial guess point. So initial guess point is suppose 1 comma 1. So by doing this we are setting the first row to be equal to the guess value. So we have defined a bunch of zeros. So at this moment this is x. Okay, in fact let me execute this and show you. So let me execute this and show you what x is. Let me go to the next cell and print out x. So all the rows are 0, but we've assigned the guess value to the first row, and we'll try to successively loop over all rows and try to iterate over various values, like the 1D case as well. We chose a guess value and then we iterated, we made successive corrections to those values and found out the root. Okay, so this is how it looks like. Let me remove this particular cell, we don't need it. Alright, so we've defined the guess values. We will define count equal to 1 for I in np.a range 1 to n iter. We will say x count all is equal to g of x count minus 1 all. Okay, we are selecting one entire row, passing it to the g function that we have defined earlier. Okay, so essentially in the very first loop 1 comma 1 gets passed to this function, the return value is assigned to this. So once we are done with this computation we have to update count, so count will become count plus 1. Okay, let me execute this, and in the end on top of this plot let us do plt dot plot. So we must plot all the xy values. Okay, so x, the first entire row contains all the x iterates, and x, the second entire the first column contains all the values of x. Basically these will have some values. In fact let me print out what x is to show you. So print x. All right, so the first column, it contains all the iterations that have happened to the values of x. The second column contains all the iterations that have happened to the value of y. So when we plot these points, this is the x coordinate, this is the y coordinate. So we must plot all the columns which are corresponding to x and all the columns which are corresponding to y. So we must do over here all rows of the 0th column x all rows of the first column. So this particular splicing, we have discussed it in the very previous lecture. This is called as splicing. So just giving a colon means it is selecting all the rows, comma 0 means of the 0th column. Similarly over here, all the rows, comma first column. And let us mark them by a black, uh, something like this, by black markers. Let us set the line width to be equal to 1. Let us see what happens. Okay, so we've started our guess over here. This point corresponds to 1 comma 1. At the end of the first iteration, it has swung to this point. Second iteration swung to this point. Third over here. Okay, so it is zigzagging its way towards the final root. All right, so we see this is the nature of convergence for a system of equations. Okay, you can try this out for a variety of system of equations. You have the basic outline of the program with you. Try to go wild with it. So one little point that I would like to impress over here is a small subtlety. Actually, we are returning over here a list. This particular thing in Python is a list. Ideally, you would like to cast it to a numpy array before passing it out of a list. So rather than having this return value, we'd rather do it np.array of this entire thing. So before returning it from the function, it would convert it to a numpy array, nothing else. It doesn't change anything, but instead of returning a list, it would return a numpy array. And lists in Python have very weird behavior, very syntactically different behavior than numpy arrays. Okay, so we have this solution. I had written down something over here. This was the original equation, and we can modify this sequence to sort of dampen out the oscillations. So how to dampen out the oscillations? So let us update the value of x partially with the old value of x itself and partially with the new value that we found out using the g function. Okay, so let me do this. Let me do x count minus 1 comma all plus this. Let me multiply it by a factor, say suppose 0.2, and correspondingly let me multiply this by the 1 minus that factor. So it's essentially a weighted sum of these two terms. Let us see what happens. So the number of the oscillations have died down quite quickly. So damping the update value allows us to reduce oscillations. In fact, let me do this 0.3, 0.7. Okay, the oscillations have dampened down even further. You're converging to the root quite fast. Let me do this. Okay, so it's converging rather fast. So this is how you can take a weighted sum between the old value and the new value. All right, so have have a go at this. Try to figure out why the behavior changes like this. Try to apply your mind to it. Try to find out the mathematics behind it. Okay, so let us proceed to Newton-Raphson iteration. So what is the idea behind the Newton-Raphson iteration? So we have f of x. So suppose we write f of x in the neighborhood of a point x naught. So we have f of x naught plus df dx at x naught times x minus x naught plus d2f dx2 at x naught x minus x naught whole squared upon 2 factorial and so on. So now when we approach the root, when we approach the root for the nonlinear equation, the so basically we are trying to solve this particular equation. So we have made a guess point around the root. So if fx is a root, so we will have 0 is equal to f of x naught plus f prime evaluated at x naught times x minus x naught. So now if we rearrange this, we can find out an expression for the root. So we have minus f x naught upon f prime x naught plus x naught, and this will be equal to x. I've just rearranged all of this. So then x at the kth iteration, or rather x at the k plus 1th iteration, will be equal to x at the kth iteration minus f upon f prime. So f and f prime are both evaluated at the kth iteration. This gives us a very easy way of sort of trying to find out a root with an initial guess. And like I've shown in the previous lecture, you also need to supply the derivative of x to the function. But in this lecture, we're gonna write it down ourselves, because later on we're gonna use certain divergent properties as well to make a entire phase plot. So it's worth our time to writing it down, and it's a really simple code. This is the code. It's just one update. Okay, so let us go over here. Let me write down what we're trying to do. Newton-Raphson method implementation. Okay, we've moved ahead of fixed point iterations. Okay, so let us define the function. So let us make a simple function. So let the function be 1 minus x squared. So we want to find out the roots. So obviously the roots are plus minus 1. Okay, so let us go over here. Let us define f, which takes an input x, and the return value will be 1 minus x squared. Let us also define df dx. It takes an input x, and let us return minus 2 times x. Fine. Let us define the x array. So x array will be np.linspace minus 2 to 2. Y array will be f of x array. Let us plot this. Okay, so this is the plot, quite obviously. So now let us write down the Newton-Raphson iterations on top of this. So let us define n iter as 10. Let us say the guess value is 0.3. All right. For I in np.a range 0, n iter, let us do x equal to x minus f of x divided by df dx of x. That's it. I mean, if we print out the values of x, so print x, so this gives us the values it goes through. So first point is 0.3, after that it shifts to 1.81, then 1.18, and then it eventually converges to 1. It converges rather quickly to the value of the root. Okay, so let us try to pictorially also draw this. So once we have the guess value, what should we do? I mean, what is actually happening graphically? This is, you should be able to tell this. Okay, you should be able to understand what is happening graphically. So this is the curve. You're making, suppose this is the guess value. So essentially you're trying to find out the tangent over here. Wherever this intersects the axis, this is the function. So then you drop the function on this, then you make a tangent over here, you end up over here, you drop a vertical over here, you draw a tangent over here, drop a vertical to the function, tangent, and something like this happens. So let us see, let us try to plot this entire sequence. So the first point that we will draw is the first point is obviously the guess value, and f of the guess value, and from that we draw whatever we have updated, comma 0. Okay, it's quite simple. So let us do this. So let us plot. So plt dot plot. So the first thing that we will plot, or rather let us draw the line directly. So the x coordinates, let us first draw this particular line. Let us draw this line. So the coordinate will be xg comma 0 to xg comma f. So in order to plot, we will first give the x coordinate. So it will be x comma x. The y coordinates will be 0 comma f of x. All right, once the updated value is obtained, let me save it to x naught. Let me save the old value in x naught. Okay, so now we will do plt dot plot. So it is going from this old value to the new value. So this is the new value, this is the old value. Okay, so the x coordinates will be x old comma x, and the y coordinates will be f of x naught comma 0. All right, so let me make this tangent to be a red line. Let me make the vertical lines to be black lines. All right, so this is how it looks. So this was the initial guess. We go over here, make a tangent. So let me also draw the x-axis. Let me also draw the, okay. So this makes things much easier. So this is the guess value. Then you draw a tangent. You drop the vertical onto the curve. Draw a tangent. Drop the vertical onto the curve again. So eventually you converge very quickly to the plot. Let us change the guess value. Let us change the guess value to minus 0.3, for example, and it obviously converges to the other root. So it all depends on where you guess. Okay, now you may think that, okay, great, Newton-Raphson iterations, they converge for all guess values regardless of what is going on, but obviously that is incorrect. It doesn't converge. You need a good guess value also, not for this particular simple case. You can go ahead and plot, you can go ahead and use this function to draw a bunch of complicated curves. In particular, there is a very famous case of x, so y is equal to x to the power 1/3. So this particular thing, the convergence using Newton iterations is quite difficult. Okay, I ask you to have a go to this, have a go on this sometime later on. So now uh, this is fine, but let us now move on to a slightly more interesting topic. It's called as basins of attraction. So we know that if we have a mth order polynomial, there will be m roots. So there is a multiplicity of roots. Okay, so if we consider just the equation x to the power um, say x cube equal to 1, suppose this equation. So what are the roots? So immediately you may say x equal to 1 is a root, and that is fine. X equal to 1 is indeed a root, but in the complex plane there are two more roots. Okay, so one is e to the power I, so 2I pi. Okay, this is what 1 is in the complex plane. Okay, because e to the power this is cos 2 pi plus I sine 2 pi. Okay, so right over here you see that this is 1, this is 0, so this is a representation of 1. So when you take a third root, x becomes e to the power 2 pi by 3 I. So obviously these are some this has some coordinates. I mean, in the Argand plane, that is the complex plane, there are points which correspond to this. So one root is this, one root will be this, and one root will be this. So there will be three roots. The third root, I mean, this is also a solution. Okay, so you can find out n pi and then divide, and then you get multiplicity of roots. This is something which you might have studied in class 11 or 12. So now let us see how we can represent all this in the complex plane. So the same technique can also be used to find out the roots in the complex plane. So simply z k plus 1 is zk minus f of k by f prime of k. So it's just a matter of replacing everything by the complex function. Okay, nothing else. So let us do that. Let us find out the following. Let us make a general function. Let us define f of z, and it will return 1 minus z square. I mean, it's just an easy case. We know that this root will still be plus minus 1. We don't need to worry so much. But I mean, depending on what this return value will be, we will obtain a bunch of complex solutions as well. Let us define df dz. It will take an input z. Let it return minus 2 times z. Let us define the iterations. So define iterate or iter f, and it will take as an input z. That is the initial guess. So once it enters with an initial guess, n iter max equal to say 100, count equal to 1, error equal to 1, error threshold equal to 1e minus 6. So the reason why I'm defining an error threshold is because I'm giving a very large number of iterations. I'm giving 100 iterations. So suppose, like in the previous problem, we gave 10 iterations, but we see that even after 4 iterations it had converged, right? So we don't want to waste iterations to make it keep converging. Rather, once it reaches a condition where suppose x10 and x11, so the difference between these two is 1e minus 6. That is the threshold that we define. If the difference between these two falls below this, we say that okay, the convergence has happened, we don't need to iterate anymore. That's why I define a bound on the error so that we can break the loop. We don't need to keep on looping till 100 iterations. Okay, so the way to do it is while error is greater than error threshold, okay, what should we do? So Zn will be equal to Z minus f of Z divided by uh, df dz of Z. The error that will be calculated will be np dot absolute. So we will find out the relative error 1 minus Zn divided by Z. Okay, so it's updating the value of Z and assigning it to Zn so that we still have the old value Z. We're finding out the absolute, the relative error between Zn and Z, and then we can update Z. So then Z equal to Zn, and we can update count as well. So once we do this, we can return the value of count. We can return the value of Z and count. Okay, so we will return Z comma count. Okay, so not only will we have actually, so n iter max doesn't make sense. N iter max in this program doesn't make sense, but we can say if the error is greater than error threshold and count is less than n iter max. So there can be a case where you're continuously iterating, but you have not reached the root. Okay, you'll keep on iterating till infinity. but you want the program to stop somewhere. So you say that unless you still not reach the error threshold, but wait, you have done sufficiently large number of iterations, so you have to stop somewhere. So that is the bit, the program bit, which will do that. So it will check these two conditions: if error is greater than error threshold and the count is less than the maximum iterations. Okay, so it will return the value of z and the number of iterations it took. Okay, so let me execute this and see there's no error. Okay, fine, everything's fine. So now let us define the complex plane. This is the complex plane. A point on the complex plane is x plus iy. Okay, so in that case, this will be x equal to np dot linspace minus 2 to 2, let's say 100 points, y equal to np dot linspace minus 2 to 2 and say 100 points, x comma y equal to np dot mesh grid x comma y. Then we will define the z matrix as x plus 1j times y. Remember that x and y are two matrices which contain all the x coordinates and y coordinates of all the intersection points. Then we assign it to z. So now let us define C as just a color array. It will sort of show the number of iterations it took for each point in that entire grid. Okay, so np dot zeros, np dot shape of x. So it is going to create a C array. So corresponding to this entire grid, we will have a bunch of x values for all of this, a bunch of y values of all of this, and for all the points on the grid, we will define a zero array C, and eventually that C will contain the total number of counts or the total number of iterations it took to reach that particular threshold that we have defined. All right, so C is this: for I in np.arange 0 comma np dot shape of z, its first value, for j in np arrange 0 np dot shape z, the first value, cj comma I. So z comma cj comma I is equal to iter f of z j comma I. So we're looping over all the values in this grid. Note it is j comma I, it is not I comma j. And think about it, why it is that way. Okay, because the rows and columns are swapped. If you move along columns, you are actually incrementing x. That is the reason why it is j comma I. And I request you to think about it. Unless you think deeply about it, it will never be clear. Okay, so cj comma I is equal to, so you're taking one point on the argand plane, passing it to the function iterf, doing all the iterations, finding out how many iterations it took for a point, for that particular point to converge to a root. The value of the root will be z. Okay, so once this is done, in fact, let me print out the values as well. So let me print out z and cj comma I, and in fact let me print out the initial or the point in the argand plane as well where we started. So it will give us the point where we have started, the converged point, and the number of iterations it took. Let me execute this. Okay, so the first point minus 2 minus 2j, it converts to minus 0.99 plus 10 to the power minus 13, so it converts to a value of minus 1. Essentially this is minus 1. It took 7 iterations. In fact, this is a very odd way of representing it. I don't want so many digits, so let me just round this off to one decimal. So np dot round z to one decimal place. Oh, much better. So we started with minus 2 minus 2j. It has converged to a value of minus 1 plus minus 1 minus j. It took 7 iterations. Then we took this value, it also converged to minus 1, 7 iterations, so on and so forth. Some of them took 6 iterations. Some of them took 7 iterations. Okay, some of them 6 iterations. Let us scroll through this. 7 iterations, 6 iterations. To reach that error threshold, it has taken 6 iterations. Oh, there are some zones with 5 iterations. Excellent. Quite obviously, there will be points in the Argand plane where the route would have been exactly that point. It would have taken no iterations. Some points have taken 8 iterations. Okay, so rather than scrolling this list indefinitely, let us in fact plot for each corresponding point on the Argand plane the number of iterations it took. Let me comment out this line. Once we exit the loop, let me plot it. So plt.pcolor. So pcolor stands for a pseudo color plot. Okay, so it's a pseudo color plot. It gives you an information about the 2D data that you have. So x comma y comma c. Let us do this. Okay, so let me add a color bar. So plt.color bar. And let me set the aspect ratio to 1. So ax equal to plt.gca, and then we will do ax dot set aspect 1. Okay, all right. So in this region there are points which took only 4 iterations, but over here they took 13 iterations. In fact, if we resolve this further, let me resolve this further, it will take a bit more time to run. It shouldn't take too much time. I'm running a fairly decently powered computer. Okay, so these are the zones where it takes a lot of iterations. These are the zones where it takes moderate number of iterations. These are the zones where it takes minimum number of iterations. And it takes minimum number of iterations because look, it's very close to the roots. It's very close to the roots. In fact, this is for z square. So what is the equation? 1 minus z square equal to 0. So essentially z square equal to 1. Let me make it cube, and the derivative will be minus 3z square. Let us see what happens. Okay, so it takes a bit more time, no problem. Suddenly, the whole situation looks a bit odd. Okay, suddenly it's not so trivial anymore. There seems to be a very weird looking braided pattern appearing out of nowhere. And if you pay close attention, there are still this zone, and this zone. These are the roots of z cube equal to 1. We know that. I've just shown you that this point, and this point, they are the roots of z cube equal to 1. Yeah, that's fine. It takes a very few number of iterations to converge in these zones. But now there's a band of zones where convergence, it takes a lot more iterations. Okay, in fact, let us zoom on this part. Let us zoom on this particular tile, 0 to 1 and 0 to 1. Let me run this cell again. Okay, so I should take 0.01 and 0.01 because having 0, that df dx causes some errors. So once we run this, we'll see a magnified portion. Okay, so I don't know if you can see this in the recorded resolution. There's plenty of things that are going on. In fact, let us try to zoom in on this particular point. So this particular point is approximately say it's a tile of 0.6 to 0.8 in the y direction and zero point 0.3 to zero point 0.5 in the x direction. Okay, 0.3 to zero point 0.5 in the x direction and 0.8 and 0.6. Let me run this. So it will do its calculation, no problem. It takes a bit of time because I've given a significantly large. Okay, so it shows a very, I mean, despite zooming into this further and further, we seem to have that braided structure. It's appearing out of nowhere. I mean, you could not anticipate from this that there will be these zones in an otherwise purple looking domain. So the purple is zones which do not require a lot of iterations to converge. But inside them, there are these link like structures. And if you even zoom in further, you'll keep on seeing these link like structures. And the orange, the purple zone is called as the zone of attraction. These blue links, they are the zones where there is no, I mean, the convergence takes a lot of time. In fact, for a very complicated form of the function that we're trying to find, there may be zones where there is no convergence at all. Okay, there may be zones where there is no convergence. In fact, let me go back to the default value. Let me go back to minus 1.5 to 1.5. Minus 1.5. In fact, instead of p color, that rendering takes a bit more time. Let me just show the let me show the array C as an image. That doesn't take so much time. Okay, so the computation, okay, let me just tell you, the computation here does not take much time. It's the p color function that takes a lot of time. Now this should run quite fast, at least relatively fast. Okay, there you go. So these are the zones where the roots are. These are also the zones where you have fast convergence. Okay, inside all those links and lobes, you have zones of fast convergence. Okay, it's a very fascinating diagram. It's not at all trivial to predict a priori. In fact, let me make this z to the power 4. So z to the power 4, you have 4 roots. Okay, you have 4 roots for z to the power 4. This is the first root, second root, third root, fourth root. Okay, so let's see. Let's not guess around and let's see what happens. Okay, so 100 iterations have been hit at several points. Okay, so these are these diagonal lines are the zones where you don't really have very easy convergence, but these locations are the points where you have fast convergence. These gaps between these weird links, they are also having good convergence. Even on these lines, you have zones of fast convergence and slow convergence. It's quite bizarre. Okay, it's quite bizarre. So lastly, we move on to the last topic, in which we want to classify this entire zone as to which route it actually converges to. Okay, right now we just know that, okay, this point takes less iterations to converge, this point takes less iteration, these points take less iterations to converge, but there's still the question whether this guess over here, so essentially we are guessing this point, and does it converge to this route, does it converge to this route, does it converge to this route, or does it converge to this route? A very non-trivial question to answer as well, and the answer is not at all straightforward. Okay, the answer is not at all straightforward. So let us make a program to see that. Okay, so now let us look at the basins of attraction. That is, if we have an argand plane and if we know that these are the roots, We want to know whether when we take this point on the Argand plane and then when we iterate it, whether this route converges to this route or this route or this route or this route. Essentially, that is what we want to find out. So let us make use of the same code. Let us reuse this code. So we don't need to plot anything. And in fact, rather than passing the number of iteration, rather than hard coding the number of iterations, let us pass it into the function. Okay, so let us take as an output the count. We want to take the count into picture. We don't want this. So this is essentially what the code is, and we have to pass the count, the n iter max as well. So we have to define the n iter max over here. So let's say it is 100. So that's the maximum number of iterations we will allow. So what we want to do is essentially take this value of z in the Argand plane, iterate it. So when it is iterated, so this is z0, then suppose you zn. So if this converged value with this error threshold is reached in n less than n iter max, then we found a root. So we must take this zn and we must insert it into, we must keep in mind that it is a root. So how do we keep in mind it is a root? We must create a root array. So the root array will contain the different roots. So root 1, root 2, root 3. So if it's a fourth order equation, there will be 4 roots and so on. Okay, so we have to store this. So because we don't know the roots a priori, if we knew the roots a priori, why would we be doing this in the first place? So we don't know the roots, so we need to define certain things. So we will define total roots, so it will be 4. So root array will be np.zeros, and this will be total roots. And remember, the roots will be complex, so we have to change the data type to complex. This is how you do it. In fact, the total roots, even if we don't know if it's a complicated function, we can define the total roots to be much more than 4. It can be some large number. The fact that we are initializing everything to 0, so it makes things much simple. You can take the total roots to be much larger. Other things will all be 0. Okay. So each time you find a root, you insert it. You insert a root if the root is not already in the root array. So initially the root array is all zeros. Suppose you take this particular point, it converges to root 1. So you take whatever this converged value will be and you insert it over here. So this will become root 1. Suppose this particular point, it converges to a different value. So then you take it and insert into this. Suppose this point, it converges to the same value. So then root 2 is already existing. So don't need to insert anything to root array. So you take all the points in the Argand plane, iterate all of them, see their convergence, and if they converge to a new root, you add it to the root array. If it doesn't, then you do something else. That's what the idea is behind the root array. So root array is this: root count is equal to 0. Then we've called this is z is the root and count is the number of iterations. So if count is less than n iter max, it means that if the number of iterations has exceeded the maximum number of iterations, we have not converged anywhere within this particular error threshold. It means that that particular point in the Argand plane took way more iterations and it probably won't converge. This means that we will assign this Argand plane point a value of nan. Okay, nan stands for not a number. It doesn't stand for a cheese naan or a butter naan. It's not a number. So if you don't achieve convergence, you will put it as nan so that in the plot it will appear as a white space. So if count is less than n iter max, what will we do? If z not in root array, so if the converged value is not inside the root array, then what do? You insert it into the root array. So root array root count will be equal to z, then root count is equal to root count plus 1. Okay, this is what you do. Now if root or if z is actually in the root array, okay, so if z in root array, then what do? So for this particular point, we converge to this root, and this the converged value for this, so the converged value, if it is r2, then we will assign this point this particular index. So the index will be 0 1 2 3. So if it converges to second root, we will assign it a value of 2, assign it a value of 1. If this value converges to the third root, we will assign it a value of 3. If this point converges to the first root, we will assign it a value of 0. So basically we are taking the entire Argand plane. For each point on the Argand plane, we are assigning it a value 0 1 2 3, depending on to which root it converges, right? And if it doesn't converge, we set it to a value of nan. When we plot this, depending on the color of the zone, we should be able to predict, or not predict, we should be able to tell that this point will converge to this value. Okay, that is what we are targeting. So if z is in the root array, then what should we do? C j comma I will receive the index. So np dot where root array equal to z. Okay, it checks where root array is equal to z and the 0th entry of this. And let me show you what the where function does, just to recall your memory. So a equal to np dot linspace 0 to 5. Let me print a. Now, not linspace, a range. So now let me print np dot where a equal to 3, or so it says a is 3 at the third point, 0 1 2 3. In fact, let me make this 2 to 10. So a equal to 3 happens at 0 1. So this is the solution, and we don't require the data type, so we need to take the 0th element of this output. So np dot where outputs it as a tuple, because there may be matrices. So we need the 0th element of this output, this function output. That is why this 0 appears. These are just syntax. I mean, the logic should be clear. Syntax follows anytime. You can always Google the syntax, but it should be clear what the logic is. So C should take the value of the location of the root. Okay. If it is not the case, if Z is not inside the root array, then what do? If Z is not inside the root array, so else Cji has to be assigned a value of nan. There you go. So this is it. This is the entire program. Let me run this. Okay, there's a small error. Let us see what has happened. Index 4 is out of bounds. Let us see what is the issue. Okay, so here's the issue. The value of z that we obtain over here, so there will be roots which look something like this, versus there will be roots which look something like this. Well, these are essentially the same root, but the fact that the computer uses a floating point representation, we have to really reduce the number of digits in order to make these roots appear the same. So z So essentially it's what is happening. Because of this, it's interpreting this and this as two different roots. So it's creating much more roots than is desired. Okay, so this is a classic mistake that this code attracts. So z should be rounded. So np.round z, and we have to round it to the first decimal place. Okay, this should now work. Excellent, it works. Let me remove this particular cell. We don't need it. Let me now plot this. So plt.im show c and plt.colorbar. Wow, this looks fantastic. So what is happening? We have four colors. uh, we have four colors over here: 3, 2, 1 and 0. In fact, let me take a screenshot of it and try to explain it in this. So what is happening? Let us see. So all the points that originate in this purple sector, they will converge to a certain root. All the points that originate in the yellow sector, they will converge to some different root. All the points that originate in the green sector, in the blue sector, will converge to their each different roots. So in case you want to know which root it converges to, we simply need to print out root array. So the purple ones, they converge to -1, the blue ones they converge to 1, the green one they converge to I, and the yellow one they converge to -I. So now look, there are pockets, there are small pockets which have different convergence properties. If you traverse across this line, you will see that, okay, if you are at this boundary, it is very difficult for you to start off at a certain point and end up in a different, in one of the particular routes, because you would expect this entire region to be converging to a certain route, but there are small zones. In fact, let me run this program and let us zoom into a certain section. Let us try to zoom in to a certain section. So say 0.2 to 0.4, and the same over here. So look, if you focus over here very closely, let me increase the resolution. Maybe that helps. 500 by 500. Okay, this may take a while, but it's worth it. So in the meantime, let us see. So there's green, then there's some pockets of multicolored stuff going on, then there's purple, then there's white. So the white corresponds to zones where there is no convergence. Okay, so the white, these two lines, you have nans, that is why they are white, they have no color. Okay, okay, much better. So there's purple over here, then again blue, then again green, yellow. So there's a multi, I mean, I don't want to call it a fractal right now, but the more you zoom in, the more these structures, they will reveal themselves. Okay, in fact, let us zoom in even more. Let us see whether we get something from this. Okay, so understanding the convergence is not at all trivial, is what I want to say. And these things are called as Newton's basins of attraction. So it is not at all trivial to tell whether this point in the Argand plane will converge to that particular route. What you have is this purple value over here, it is still converging to -1. This thing is still converging to -1. this thing is also still converging to -1. Okay, the green one was converging to 1, so this thing is converging to 1. These all regions are converging to 1, no doubt. This is converging to 1, 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 and there are small zones inside this as well. The more you zoom in, there will be even more zones of small, very small pockets of green as well. They will also converge to 1. Look, the structure becomes even more bizarre. So over here, there's another series of colors that will happen, and the more you keep on zooming in, the more this bizarre structure will begin revealing itself. This white line is the zone where not even a single value will converge. All the points on the diagonals, they will diverge. Okay, so if you guess on this line, you will not get anything. So yeah, this is what I wanted to discuss. I hope you've learned something new. If not, you've seen how to create such complicated plots with the help of very easy programming. And I'll see you next time with another lecture on nonlinear dynamics. Until then, it's goodbye from me. Have a nice day. Bye.